Hello, today we're going to talk about types of energy. I've written a couple things down here. If you want to pause the video and just briefly write them down, there's things that were already discussed, so go ahead and do that. All right. So, real quick, what we discussed so far is work is a change in energy. That's this first part here. All right. So, work is a change in energy. We calculate that by taking force times delta x. Work can be positive or negative. If the force is with the motion, its work is positive. If the force is against the motion, the work is negative. The units for work and energy are joules. Okay. So let me write that a little neater. All right. So the units for work and energy are joules. Okay. And you can think of energy, and I mentioned this in a previous video, but energy is kind of like the damage that something can do. And we're going to talk a little more about that today. We also talked about dissipated energy. That's friction times delta x. That's almost always negative. And what friction does is take energy away from an object and creates heat out of it. So you're taking energy out and making heat. Okay. Now, the other type of energy that we have already discussed is elastic, and I'll put that over here. So elastic potential energy. And that is E, a little e, and that's the energy that a spring or rubber band has when it's stretched or compressed, and that is 1/2 kx squared. And you guys had labs on that, and you also did a sheet on that. Again, energy always measured in joules. In this case, K is a spring constant. Okay, and X is how far you've stretched the spring, and you always got to make sure that's in meters. Okay. Well, there are two other forms of energy that we're going to talk about. The next one that we can talk about is the energy of motion. And that is called kinetic energy. And I mentioned this before, if two bowling balls are coming at you, one's going 10 miles an hour and one's going 20 miles an hour, you know that the one that's going 20 miles per hour is going to cause more damage, right? Also, if I toss a golf ball and a bowling ball towards the same speed, you know the bowling ball is going to do more damage than the golf ball. So those kind of tell you the things that are involved with kinetic energy. Kinetic means moving, so that's why we call it kinetic energy. The symbol we use for kinetic energy is E sub k, okay, energy kinetic, okay. And there is a long derivation of this, but I'll just give you the result. Actually, it's not a long derivation, but there is a derivation for this, and you can look that up online if you're interested. But the equation you get is 1/2 times the mass of the object times the velocity of the object squared. Now again, be careful. M is mass, and that's got to be measured in kilograms. So if you're given a mass in grams, make sure you convert to kilograms. V is velocity, and that's got to be measured in meters per second. That's simply how fast the object's going. Okay. Now, I won't do an example where I plug numbers into this. You're going to do that on your practice sheet. But I will mention a couple things. Let's say I gave you an object and I had a certain amount of kinetic energy because it's moving, right? And let's say I double the object's mass and don't change anything else. By what factor will the energy change? Well, in that case, if you're doubling the mass and nothing else is changing, then you're going to double the amount of energy. Okay. On the flip side, what if I said you take an object and you double its velocity? By what factor does its energy change? Well, there the v is doubling. And you'll notice that it's v squared. So you would take 2 squared, so the energy would actually quadruple, be 4 times as big in that case. Okay. Now you'll do some practice with kinetic energy on your sheet, but otherwise it's pretty easy. Okay. The final type of energy I'll discuss today for a brief moment is called gravitational potential energy. Okay, and basically that's the energy something has due to its height. So if an object has height, it's got gravitational potential energy. Now, more formally, what it really means is when two objects are separated. Um, Now, for our purposes, one of the two objects is always going to be the Earth. So, for instance, let's say you hold your textbook up. Your textbook is now separated from the Earth, so we say the textbook has potential energy. Technically speaking, the potential energy is really the Earth-book system. It's in the gravitational field between the book and the Earth. But for our purposes, we're just going to pretend it's all in the book. So when we say we lift something away from the Earth, we say it's got potential energy, gravitational potential energy. Um, Now, if you imagine the work that you would need to do to lift your book, well, work would be force times distance. So that's this equation right there, force times distance. If you're lifting your book at a constant velocity, then you're applying a force equal to the weight of the book. And that would be the force of gravity. And the force of gravity equals mg. So the work done to lift the book would be mg, that would be your force, times delta x, okay? So we kind of rewrite that and we say, we call that energy gravitational, and that's gravitational potential energy, and it's equal to the force, which is mg. And instead of saying delta x, since we're going up and down, we call it height. Okay, so mgh. So that's the equation for gravitational potential energy. Again, make sure your mass is measured in joules. Make sure your acceleration of gravity, that's little g, on Earth at the surface, that's 9.8 meters per second, and that just represents the acceleration of gravity. And then h represents the height. The book is above something, and you got to make sure you measure that in meters. Okay. Now, there is a note, an example I want to do with this because it can get a little tricky as far as what the height is. So let me give you an example. So let's say you're in the classroom or something, or you're at home, and let's say here is the floor, and here's a desk in your room, okay? And here's a book on the floor, and you're going to lift the book 3 meters up. So we'll call this total height 3 meters from here to here, okay? Let's say the desktop is 1 meter high, okay, from the floor. All right, so what we're going to do is we're going to calculate the change in gravitational potential energy from the floor to the ceiling. But we're going to use two reference points. We're going to use the floor as one reference point, and we're going to use the desktop as the other reference point, okay? Now for the floor, the beginning height of the book is 0. So if I do mass, I got to give you a mass of the book. Yeah, let's give it a mass of, let's see. We'll give it a mass of 10 kilograms, okay? So it's a heavy book. It's like your book bag, okay? So if you're on the floor at the beginning point, we'll call this point A, and we'll call the end point point B. At point A, well, you have 0 height, so your energy gravitational would be 0, okay? At point B, your gravitational potential energy would be mgh, your mass is 10, gravity is 9.8, and the height is 3, okay? And if you multiply those out, 30 times 9.8, you get 294 joules, okay? What about if I measure everything from the desktop? Well, if I measure from the desktop, what's the starting height of the book? Well, it's below the desktop. The starting height is negative, okay? And so E sub G would be M, which is 10, times G, which is 9.8. Well, point A is 1 meter below the desktop, so we would put a -1 here, and you would get negative 98 joules. And how about at point B? Well, you still have a 10, you got 9.8. What's your height from the desktop to point B? Well, that's 2 meters, so you put a 2 here, and you would get 196 joules, okay? Now, why am I doing all this? Well, let's look at the change in energy. For this first example, the change in energy was you do final minus initial. So it'd be 294 minus 0, and that is 294 joules. How about for this guy here? change in energy would be the final, which is 196, minus the initial, which is negative 98. So what you're doing is 196 minus negative 98, which is 196 plus 98, which is 294 joules. So the whole point of this example is to show you that it doesn't really matter what you call zero height. You can make any point on the picture zero as long as you measure everything from that zero that you pick. So if you say, I want the ground to be zero, just make sure you measure all your heights from the ground. If you say, I want the desktop to be zero, that's fine as well, as long as you measure all your heights from the desktop. This will come into play a lot more in the future. In each problem you're given, you have to decide what you want the height zero to be, okay? And then you measure everything from there. One last thing I'll mention, both gravitational potential energy and elastic potential energy are called potential energy. What that means is potential energy has to do with things separated. So for gravitational potential energy, the book's separated from the Earth. For elastic potential energy, that's a spring. When you pull the spring apart, the little molecules of the spring are separating apart. Potential energy is the energy of that separation, that position. And that potential energy is stored. You can get it back. So for instance, if you let the spring go, it pops back in and makes motion. Or in this example we just did now, if you drop the book, that makes motion. So potential energies are energies that are stored up that you can get back. You can get it back. We will talk a lot about that in future discussions. I hope this was useful, and good luck on the sheet.